Elena and Mohammed are wearing ice skates and standing on an ice rink. The reason that we want to describe the problem on an ice rink as opposed to maybe concrete or asphalt or grass is because it's a example where the coefficient of friction is pretty much equal to zero. So if friction isn't present, then there are no external forces acting on the system, and that describes what we call an isolated system. Momentum is conserved for isolated systems. The system also has to be closed. A closed system is just one in which all of the mass has been accounted for. So the mass of the system is partially due to the mass of Elena and the mass of Mohammed. His hat isn't going to go flying off. Neither of their skates are going to go flying off. All of the mass that's in the system to begin with remains in the system. So the process is the two of them pushing off of each other. Remember, Newton's third law says nothing can be touched without being touched in return. So we could say the force that Elena exerts on Mohammed is equal and opposite to the force that Mohammed exerts on Elena. From now on, we'll just use the symbols 1 and 2. The force of object 1 acting on object 2 is equal and opposite to the force of object 2 acting on number 1. When we multiply both sides of that expression times time, we're saying that the impulse for object number 2 is equal and opposite to the impulse for object number 1. Impulse is also change in momentum, so the change in momentum for object 2 is equal and opposite to the change in momentum for object number 1, which means if I add the change in momentum for object 1 to both sides of the equation, we can say the total change in momentum is equal to 0. And that's what we mean when we talk about the law of conservation of momentum. So this is a problem in recoil. Two parts of a system start out together, a force is applied, and they fly apart in two different directions. The initial momentum of the system is equal to the final momentum of the system. That's consistent with a statement that says the overall change in momentum is 0. Well, the initial momentum in this system is 0 because both Elena and Mohammed start out at rest. So the final momentum also has to work out to be 0. Don't let that confuse you. We're going to make a frame of reference that says motion to the right is positive. So when they push off, Mohammed will have momentum to the right. Elena will have just as much momentum to the left, but that's an amount of negative momentum. So Elena's negative momentum after the collision will be canceled out by Mohammed's positive momentum, and so the final momentum of the system will indeed be 0. That's not to say that Elena and Mohammed will have equal velocities as one another, because they don't necessarily have the same amount of mass. So let's make up some numerical values and say the mass of Elena is 50 kilogram and the mass of Mohammed is 70 kilogram. Okay, so what we want to know is what's the final speed of both of them after they've pushed off. So let's assume that when they push off, Elena, as a result, flies back in this direction with a velocity of, how about 6 meters per second? Ooh, that's pretty fast, but let's go with it. So what's going to be the final velocity for Mohammed? Initial momentum has to equal final momentum. We could say then that the mass of Elena, or the mass of object number 1, times the initial velocity of object 1, plus the mass of object number 2, which is Mohammed, times the initial velocity of object number 2, is equal to m1 v1 plus m2 v2. When I multiply mass times velocity, I get momentum. So I'm finding the momentum of object 1 and number 2 added together, which is the overall initial momentum. Actually, I just thought of a better way to write this. I don't like having so many subscripts. So I'm going to replace the symbol V with U. From here on, U is going to be a symbol that represents initial initial velocity. Right? Any speed that we know of before an interaction between the particles in the system, and v will be the symbol for final velocity. So let's rewrite this two-body conservation of momentum equation one more time. We can say m1u1 plus m2u2 has to equal m1v1 plus m2v2. Of course, in this case, these are both equal to 0. So we find that m2v2 has to equal negative m1v1. That means that the velocity of Muhammad after the collision is equal to negative the ratio of their two masses multiplied by the velocity of Elena after the collision. So the velocity of Muhammad is equal to negative 50 kilogram divided by 70 kilogram multiplied by 6 meters per second. The negative just indicates that Muhammad's moving in the opposite direction. Time out. We've made a mistake. Scroll back up. When we stated that Elena's final speed is 6 meters per second, we have to rectify that with our frame of reference that says to the right is positive. So let's scroll back down and see where we made our mistake. Here it is. The final velocity of object number 1, which is Elena, is to the left, so that's a negative 6 meters per second. This is the biggest mistake that students make, and professors sometimes, regarding the law of conservation of momentum, failing to assign negative values for velocities that are moving in the negative direction. Okay, so the negative in this part of the equation, and that negative will cancel out. And so the final velocity for Muhammad is equal to 5/7 of 6, which equates to positive 4.3 meters per second if we round off to 2 sig figs. And there you have it.